All right, let's dive right into this explainer. We spend a ton of time talking about how artificial intelligence understands language, right? Or how it remembers context. But there is this absolutely fascinating mechanical reality that happens at the very end of that process. After all the understanding and remembering is done, the model actually has to output words. So today, we're exploring Tier 4, how AI speaks. We are going to trace the exact journey from that hidden internal meaning straight through to the visible words you eventually read on your screen.
Here's our roadmap for today. First, an introduction to AI speech, followed by generating raw token scores. Then we'll look at decoding and sampling options, jump into sampling controls and filters, talk about ending sequences and style, and wrap it all up with the final expression.
Okay, Part 1. Introduction. The AI Speech Foundation.
Looking at this flow map, we can clearly see the exact architecture of this whole process. It's like a highly structured pipeline. It all starts with the foundation, using the output layer and softmax. From there, it flows right into decoding options, like greedy versus sampling. Then we apply our sampling controls, things like temperature or top K and top P filters. Now, if it needs to, the model uses advanced decoding, like beam search. And finally, it routes through stopping and style via stop tokens and tone, ultimately arriving at closure or the full expression. Moving right along to Part 2, raw token scores and output layer mapping.
Let's talk about a concept called Logits. Basically, the final layer of the AI transforms all of its internal hidden thoughts into these Logits. Now, what are they? They're simply the raw scores for every single token in the AI's entire vocabulary. A logit essentially says, hey, here are all the possible next words, and here's exactly how strongly the model leans toward each one. Higher logits mean more likely tokens, lower logits mean less likely ones. These raw scores are literally the bedrock for probability and word selection. So just picture these raw token scores as varying heights on a bar chart. The model is constantly evaluating these unnormalized scores, rising and falling for every possible token. But here's the catch. Raw scores are just that. They're raw. To actually make a decision, the model has to prepare these unnormalized logit scores to become actual probabilities that it can work with. And that magical transformation? Well, that happens through something called softmax. Softmax is this neat little function that takes those messy, unnormalized logits and converts them into smooth, clear probabilities that the model can actually sample from. Once softmax does its thing, higher probabilities clearly point to the most likely next tokens. The raw scores have officially become choices.
Which brings us to Part 3, decoding and sampling, picking the next word.
Okay, the most straightforward method here is called greedy decoding. And honestly, it's exactly what it sounds like. Greedy decoding always selects the most probable token, the absolute top choice, every single time. So what does that mean in practice? Well, it's incredibly fast, it's totally deterministic, and highly predictable. But because it always takes the most obvious path, it often sounds pretty repetitive. It's important to remember, though, greedy decoding is just one option. It is definitely not a required step. Let's compare that super direct choice with an alternative, sampling. While greedy decoding always rigidly picks the top token, sampling actually chooses from several likely tokens instead. And this is a real game changer because it introduces controlled randomness into the system. It lets the model pick from the top few tokens based on how strong their probabilities are. This is exactly what creates variation and flexibility. In fact, this is the exact reason why you can ask an AI the same question twice and get two completely different answers. It's just sampling a different path through the probabilities to give you much more natural-sounding text.
All right, Part 4, controls and filters, guiding the randomness. Now, the most famous of these controls is definitely temperature. Temperature is a setting that fundamentally reshapes the probability distribution. It basically answers a very human question for the machine. How wild or calm should this output be? This one setting alone is the entire reason an AI can write both a perfectly dry, predictable legal brief and a completely wacky, unpredictable poem. Think about it like this. A low temperature setting creates a sharp, focused, and highly deterministic output. It forces the model to play it safe. On the flip side, a high temperature setting yields a diverse, creative, and much more unpredictable output. The model feels completely free to choose those slightly less probable, but maybe way more interesting words. Once that distribution is reshaped by temperature, the model has to ask itself, okay, from this new distribution, which tokens should we actually keep? Enter top K and top P. And I really want to emphasize this point. These are filters, they are not shapers.
Top K means the model is going to keep only the top K number of tokens to choose from. Top P means it'll keep tokens until their cumulative probability reaches P. Both of these methods filter the token space just to make sure the output stays coherent, while still allowing for that fun, controlled randomness.
But hey, what if you don't want creativity at all? What if you want the absolute mathematically best sentence possible? For sure, that's when you'd use an advanced decoding method called beam search. Beam search actually evaluates several possible sequences or parallel paths all at once. It keeps the strongest candidate paths as they build up and actively throws away the weaker ones. This is incredibly useful when your main goal is getting the absolute best scoring sequence overall rather than just nervously picking word by word.
Moving on to Part 5, Ending and Style, Knowing When to Stop.
An AI doesn't just trail off awkwardly into silence. It uses stop tokens and specific stopping rules to end its generation. The model will stop either when it hits a predefined length limit or, and this is the cool part, when it actually predicts completion. Producing a stop token ensures a very clean, intentional ending to the entire sequence. And as it wraps up that sequence, we naturally perceive how the model sounds. But remember this, and it's absolutely crucial, tone is not emotion. It is purely a statistical pattern. A model's style comes entirely from its training data combined with those decoding settings we just talked about. Those sampling choices literally shape exactly how the AI speaks and dictate whether it sounds calm, highly technical, or super expressive.
Finally, Part 6, the final expression. Meaning becomes text.
For the AI, the act of speaking completes its cognitive loop. All those memory vectors and internal states finally flow out into a text stream. The AI transforms all of that deep internal meaning into fluent text, executing this massive, beautifully complex pipeline just one single token at a time. So when you read a beautifully crafted paragraph from an AI, you aren't really reading thoughts. You are reading math. This is how AI speaks, by decoding, sampling, and selecting each next word. It really leaves us wondering, doesn't it? As these models get faster and their vocabulary becomes even more nuanced, is there really any difference between a perfectly calculated statistical pattern and true expression? Think about that next time you see the cursor blinking.